Okay, let's do the key for the electrochem homework. So just to start, just to re-emphasize, let me get my pencil to connect. Hopefully it has a charge. Nice. So this table here is an example of the standard reduction potentials for a bunch of different half reactions. We call them half reactions because if you have reduction, you have to have another reaction where oxidation is occurring, right? But all of these are written as reductions. Remember, if you flip any of these reactions, the sign of the voltage will change. Okay, so let's get started. The first thing is that we're given two half reactions, aluminum plus 3 electrons and nickel plus 2 electrons. So I think one of the trickiest parts about this unit, one of the tricky things, is making sure you're looking at the right information. So let's find these reactions in our table. So we have the aluminum one here, and we have the nickel one here. Now I want to caution you, right, as an example, here is a copper one, and here is a copper one. They look very similar, but notice we're adding 2 electrons here and 1 here. So you just want to make sure you're dealing with the right reactions. So it says sketch the galvanic cell, identify the metal in each electrode, label it all, yada, yada, yada. The important thing here is that it says galvanic cell, right? And what does that mean? By definition, that means that the voltage for the cell must be greater than 0. Right? That's what a galvanic cell is. So why is that important? Because that's going to tell us which one of these two reactions here is going to be oxidation and which is going to be reduction. We figure out which one is reduction and oxidation using this idea. So as an example, we know that E cell is calculated by taking the voltage of the cathode and subtracting the voltage of the anode, right? And so we have two scenarios here. Scenario 1, scenario 2. Scenario 1, we'll have aluminum as the cathode and nickel as the anode. Here we'll have aluminum as anode and nickel as cathode. So E cell here would be equal to the cathode, which is negative 1.66 minus negative 0.23. Well, in this example, E cell is still negative, right? So this probably is not what's going to happen. But let's just check. Here, we would have the cathode, which is negative 0.23 volts minus negative 1.66 volts. Well, I hope that you're seeing that this definitely would result in a positive cell voltage. And I'm just trying to get my calculator out of my bag. Hopefully it's in here somewhere. Here we go. Okay, right, so this ends up being negative 0.23 minus negative 1.66, which is positive 1.43 volts, right? So the point here is that we had to do this to figure out how to draw our cell. What's the anode? What's the cathode? Okay, so let's take all of this, shrink it, and put it right over here. Now let's draw that galvanic cell. So it's 2 compartments. We know the anode is always on the left. This is where oxidation is happening. This is the cathode. This is where reduction is happening. And we now know that the aluminum is at the anode and the nickel is at the cathode. So this will be aluminum. This will be nickel. They're connected by a wire. The electrons always go towards the cathode from the anode. We're going to have our little salt bridge. It doesn't really matter what you put in it. A good option is just potassium nitrate. And then you can come up with your own solution. So here we'll just do aluminum 3 plus, and then we can just do nitrates are always a good bet. Here we've got nickel 2 plus. No problem. So it says label the solution, right? It doesn't really matter what the counter anion is in this example. Show the direction of the electron flow, show the direction of ion migration through the salt bridge. So if oxidation is occurring here, that means that solid aluminum is being converted into cationic aluminum, which means that the negative nitrate needs to move in as this solution is becoming more positive. Here, we have nickel 2 plus depositing onto the solid nickel electrode, which means it's losing positive charge in the solution. So we probably want our potassium ions to migrate into this solution, right? This side's oxidation, so we have aluminum oxidizing to this, and here we have reduction happening. So this is what's happening. Okay. All right. Cathode, anode. Okay, so that's looking pretty good there. Write the overall balanced reaction. So we know now that we have aluminum. Oh, this should be 3 electrons. 3 electrons, and we also have here. Now, you would normally just add the reactions together, but you have to notice something here. The electrons don't match up. We have to get them to cancel out. So to do that, let's multiply this top one by 2 and this one by 3. So what we end up with is 2 aluminum solid plus 3 nickel yields 2 aluminum 3 plus 3 nickel solid. And you can check if this works because the charges should equal each other. So we have positive 6 and positive 6, 2 aluminums, 3 nickels, 3 nickels. Determine the standard cell potential. Well, we did that already. It's 1.43 volts. Right, we did that in order to draw the galvanic cell. Give the standard line notation. So we always start with the anode. So it would be aluminum solid. You have a phase boundary between the solid aluminum electrode and the aluminum ions. Then we have our salt bridge. Then we have our nickel ions being reduced onto the solid nickel. Okay, number 2, given the line notation, determine if the non-standard cell potential will be greater or less than the standard cell potential if, right, the magnesium ion concentration is 0.1 and the aluminum ion concentration is 1. And here is the Nernst equation. So first of all, let's look at this. We know that the anode is here on the left and the cathode is here on the right. So this is oxidation. This is reduction. So what are our reactions that are happening? We have magnesium solid going to magnesium 2 plus with 2 electrons. And we also have aluminum being reduced to give us aluminum solid. Now let's find the overall reaction. Again, notice the electrons in each half reaction don't match, so we have to get them to cancel out. So let's multiply this top one by 3, this bottom one by 2. So our overall reaction is going to be 3 magnesium solid plus 2 aluminum trication yields 3 magnesium 2 plus 2 aluminum solids. Now, the reason why we needed to do this, to get this reaction here, is because of Q. What is Q? Q is the reaction quotient and is defined the same way as the equilibrium constant, right? But it's just at some time point that is not at equilibrium. So if we wanted to write out an expression for Q, you would look at your overall reaction. Okay? Now, what states of matter don't show up in our equilibrium statements? The solids. So what this is going to look like is the concentration of magnesium over the concentration of aluminum. But be careful, that's not the full story. You have to make sure you're paying attention to stoichiometry. So this is going to be magnesium cubed and aluminum squared. It's not so important to answer this question necessarily, but it's still something you should be paying attention to. That is a very common mistake that is missed on the AP exam. So what's the point here? What's happening? It tells us these concentrations. It says Q would be 0.1 cubed over 1 squared. So this is going to be a number that is, we'll say Q is less than 1. Right? It's definitely going to be a small number. So the natural log of 0.1 cubed over 1 squared is going to be less than 0. It's a negative number, right? That's the same thing as saying, the natural log of a fraction is negative. So because of that, what the Nernst equation is going to start looking like is we have the non-standard cell potential, right, which we know is non-standard because it doesn't have that little knot. We have the standard cell potential, and then this is going to end up being a minus here. So minus RT over NF ln of Q. The reason why we have a negative sign here is because the natural log of a number smaller than 1 is going to be less than 0. So what this means is that the non-standard cell potential E will ultimately be less than the standard cell potential. So what you could say is the potential of the cell will decrease, essentially, right? And that's our answer. Okay, moving on. Number 3, it says, given the standard potential for the reaction, yada, 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 it gives us a nice cell potential, basically. Calculate the standard potential for the following reaction. So you want to think, how did they get this reaction? Well, what I'm seeing is that first they flipped it, or maybe they didn't flip it first, but it was flipped. And so how does that affect the cell potential? Well, that's going to flip the sign. So now it's negative 1.23 volts. Then it looks like they multiplied by half. But unlike in Hess's law, does multiplying and changing the stoichiometric coefficients affect the cell potential? It does not. That is one of the tricky pieces of this unit. So it's still negative 1.23 volts. Even though they multiplied, it doesn't matter, right? So the answer is D. A was obviously put there. I don't know why A was put there. But choice C would probably be your next best choice because I bet that's half of 1.23, but that's not actually right. So be careful. Okay, number 4 says, on the diagram, indicate the direction of electron flow on the wire. And so you're like, well, what's going on here? Well, the first thing that I'm seeing is that there are lots of bubbles coming off of this electrode here, right? Bubbles in water or in a liquid, to me, that indicates gas evolution. Look at your 2 reactions that are given, your 2 possible reactions. Do you see anything that's a gas? I see liquid, aqueous, solid. Oh my goodness, look at that. Gas. The only gas. So just from looking at the image, not understanding anything about electrochemistry, none of that stuff, right? I can already tell you that at this electrode right here, the reaction is 2 waters are liberating molecular oxygen gas, as indicated by the bubbles in the picture, plus 4 protons, plus, let's see if I can move this, 4 electrons. Now, this reaction, hopefully you're seeing, is an oxidation reaction. You're like, Mr. Hicks, well, how do you know that? Oxidation reactions are when electrons are liberated, right? Something lost some electrons. Well, look at that. 4 electrons liberated, vive la France, right? So they also tell us, too, that this is the reaction that's happening here, right? So nice. This is very clearly a reduction. If you have a cell, you have something that's reduction, you have to have something that's oxidation. Anyway, so we know that oxidation is where the electrons are coming from, right? Because this is our anode. So the electrons are going this way. The electrons are heading towards the cathode, which is where reduction is occurring. Now you're like, wait a second. Isn't it true that we always put the anode on the left? Well, yes, that is a convention, which is used by scientists, chemists, just to make diagrams a little easier to interpret, but that doesn't necessarily mean it's always going to be that way if they give you a diagram, right? That was the point of this question, was to figure out which side is the anode. So let's write a balanced net ionic equation for this electrolysis reaction. What is electrolysis? Electrolysis is just an electrochemical reaction that is powered by some outside source. So maybe a battery, you plug something into the wall. It's really not that different. So the most important thing in a balanced net ionic reaction for electrochemistry is that the electrons need to cancel out. So what are our two reactions? We have the reduction of copper to copper solid, and we're also oxidizing water, which is a very important reaction in alternative energy research. Hopefully you're noticing very quickly that the number of electrons are not equivalent in the two half reactions. So we need to do something. Now here, this is probably the first time we're seeing this example where we don't need to multiply both reactions by something necessarily. We just need to multiply this top one by 2. I guess technically you could say we're multiplying this one by 1. Anyway, if we add this together, we get 2 copper cations plus 2 waters yields 2 copper solid plus molecular oxygen and 4 protons, right? The electrons cancel out. So this is our full balanced net ionic equation. Okay, we weren't able to go over this in class, but this is an example of an electrolysis problem. And the name of the game here is dimensional analysis. You have to make your units cancel out. And in order to do that, we need to know that amps are given units of coulombs per second. C is for coulombs, which is really just a unit to measure electrical charge in the same way that meters is a unit to measure distance. And it also tells us that tells us what F is, which is called a Faraday. And the reason why we use Faraday's is because it's just a really nice number to show us how much charge is in a mole of electrons, right? Electrons have a negative charge. It's a number, 1.602 times 10 to the negative 18. But what if you multiply that number by Avogadro's number? Well, what you'll get is 96,485 coulombs, okay? So let's see what happens here. It says an electric current of 1.5 amps passes through the cell for 40 minutes. Calculate the dry volume in liters measured of all the stuff of oxygen that is produced. So hopefully you're seeing that ultimately we're going to need to use Pervnert because we're dealing with a gas. But first we need to basically figure out how many moles, we'll see, so goal 1, determine moles of molecular oxygen produced. 2, use Pervnert to calculate volume of oxygen given that information, right? So if you had trouble with this question, maybe pause the video and try and rework this now that you maybe have a slightly better idea of what you're trying to do. So let's start with goal number 1, calculating the moles of oxygen. So I think it's good to always start with the current. So we have 1.5 amps, which is coulomb per second. Now, where in the question do they give you another time variable? They give you 40 minutes. So we have 40 minutes. Minutes and seconds don't cancel out. So we need to convert minutes to seconds. So we know that, let's say 60 seconds is in 1 minute. Now let's start rounding up our units, right? Dimensional analysis is key here. The minutes cancel out, the seconds cancel out. Amazing. So now we're just left with coulombs. Ooh, right? But how can we relate coulombs to oxygen? Well, if you look at your balanced net ionic equation, do you see any coulombs in this equation? No, you don't. But do you see something maybe like some connection between oxygen and maybe electrons? Well, yeah, if you look here, let's see, what color should we use? Let's use red. We have oxygen for every 4 electrons. So if I can go from coulombs to electrons, I can go from electrons to oxygen. So let's use Faraday's constant. So we know that we have, coulombs is in the numerator. So I'm going to have 1 mole of electrons for every 96,485 coulombs. Then from our half reaction with oxygen, we know that it's 1 mole of oxygen, right, for every 4 moles of electrons. And I think this is maybe the hardest part, this right here. These are from the stoichiometry of that half reaction. Anyway, so now we have moles of oxygen. That's fantastic because everything else cancels out. So let's put that in our calculator. I do 1.5. If you're wondering how to put this in your calculator, multiply everything in the numerator, hit enter, then hit answer, divide, and then do parentheses, and then multiply everything in the denominator. So 1.5 times 40 times 60 divided by 96,485 times 4, which gives us 9.33 times 10 to the minus 3 moles of oxygen. Fantastic. Now it's something you should be super familiar with, which is perv-nert. So we're trying to find volume. It tells us the pressure is 1.16 atm. We know moles, so it's 9.33 times 10 to the minus 3rd mole. We know R, which is 0.08206 liters, atmospheres, mole, Kelvin. And it gives us a temperature of 25, which is 298 Kelvin, I believe. Yeah, 298 Kelvin. So just solve for volume. So let's do that in the calculator really quick. Times 0.08206 times 298. Divide all that by 1.16. We get a volume of 0.196, or I guess, let's see. It's looking like 3 sig figs, so maybe 0.197 liters. Is that what it wants? Yep. Bada bing, bada boom. There you go. All right. So that is the electrochem homework key.